Not many people enjoy the noise of an alarm clock in the early morning. However, it's very effective to wake you up. Sound has many functions. Besides warning us, we also use sound as our primary way of communication. Besides, sound also can be pleasant, for example when playing music. However, there is also the type of noise that is neither pleasant nor useful. Traffic noise, loud machines in factories, etc. In 2018, the World Health Organization published an extensive report in which the connection between noise and health risks were established. It turns out that excessive noise can not only make us deaf, but also can impact our mental and physical health in other ways, such as a chronic lack of sleep and an increased chance of getting cardiovascular diseases.
My name is Sjoerd van Ophem and I'm a postdoctoral researcher here at the KU Leuven in Belgium. And the aim of my research is on the one hand to minimize noise when it could cause health problems, while on the other hand making sure that we can enjoy and use sound when it's beneficial to us. In particular, I'm looking at sound that is caused by structural vibrations. Many products that we use in our daily lives produce sound that is caused by structural vibrations. Examples are your smartphone, guitar, etc. To battle the excessive noise or maximize the impact of the desired sound, we need to understand the physical behavior which can be predicted using models.
To understand how we should model sound, we should first look at what sound waves are. We are all familiar with water waves, but sound waves are a bit more difficult to picture since they act on air particles that are too small to see. Whenever a sound is made, for example when we perform a snare drum roll, air particles start to vibrate, leading to a wave. When this wave reaches our ears, they make our eardrums vibrate. Thus, to make a computer model that correctly models sound, we need a model that captures this wave behavior. How can we do this? We start from a mathematical equation that describes this wave behavior, the wave equation. Ideally, we would solve this equation to find out the behavior of the sound wave. It turns out that this is a complicated thing to do. Only for a few specific instances the analytical solution is known. However, to know how the wave travels in a complicated environment, such as the interior of a car or an office space, the analytical solution is not known. So what to do?
Luckily, in recent decades, computing power has increased dramatically, which means that we are now able to solve this problem by using computer models. Starting with a digital representation of the object, this object is cut into small little elements, which we call finite elements. And these finite elements are then forced to weakly adhere to the wave equation. Then we end up by combining these elements with a set of linear equations that we can easily solve in our computer, and that gives us an approximate solution to a problem. The problem with these models is that even by today's standards, they require a huge amount of computing power. Let's say you would want to do real-time sound prediction on your smartphone. This is not feasible. In my PhD thesis, I focused on a solution to this problem that works with the concept of model order reduction. To show you what I mean by that, let's go back to another example.
In this example, I show a simple model of a rectangular room. Again, the model is chopped into small elements and the solution is calculated. A naive model order reduction approach would be to increase the size of the elements. This would definitely lead to a smaller computer model. The thing is that the model still allows for solutions at higher frequencies, such as the following non-physical solution. The philosophy of model order reduction is to throw away all of this unneeded information out of the equation. In particular, my research interest is focused on the modeling of exterior vibro-acoustic problems. That is, problems that are unbounded in a certain direction. An example would be the noise coming from a rock concert happening around the corner of your house. The tricky part about the resulting models is that we cannot chop our problem in an infinite number of elements in the unbounded direction. Instead, a known solution is to limit the number of elements to a certain distance and then apply a boundary condition on the edge that approximates the unbounded domain. This extra boundary condition leads to additional challenges from a model order reduction point of view, such as stability in the time domain. In my thesis, I derived a method to apply model order reduction on this problem that retains time stability. The model uses infinite elements on the boundary of the finite element mesh. As the name suggests, these elements extend to infinity to approximate the unbounded domain. The proposed strategy leads to models that are super small. To give you an idea, from models with tens of thousands of variables to less than 100 variables, while retaining the desired accuracy. By itself, this is already a very useful result, since it gives scientists and engineers a tool for the rapid calculation of complex vibro-acoustic models. An example could be the detailed modeling of a speaker cabinet for designing the best possible sounding speaker. Besides pure modeling, another interesting approach is to smartly combine the numerical model with a small set of real-life measurements and get the best of both worlds. The small set of measurements gives us information on the real physical system, while the numerical model gives us the opportunity to also calculate the vibro-acoustic behavior on points where we don't measure. Thus we are effectively creating a virtual sensor. For example, we could use this concept to create a virtual microphone on a location where it is practically impossible to put a real microphone. The creation of a virtual sensor is possible through a process called state estimation. An essential part of this virtual sensing scheme is to have a numerical model that is compact and can be evaluated in near real time. Thus, here is where the reduced order models that I derived come into play.
During my PhD, I took this structure, which is a deep-drawn structure that represents an oil pan, to see what is the sound radiation from the structure. Now let's put it in a room that we can accurately model with our exterior vibro-acoustic models. We are now in a semi-anechoic room, and as you can hear, it's very silent here. In fact, the only reflections in this room come from the floor. All the walls are made to absorb sound. Thus, we can perfectly model this with our exterior vibroacoustic model to, for example, determine the sound that's radiating from the structure if I hit it with a hammer. Due to the deep drawing process, the structure is very difficult to model accurately. We compared a few time domain microphone measurements with time domain data coming out of the numerical model, and the results were off.
However, after this step we built the virtual sensor. We used a finite element model combined with infinite elements and reduced it in size. We took a small set of microphone measurements, in this case 5 locations, and we measured the input force. Then we checked the virtual pressure measurement against the real one, which leads to the following results. Thus a very good match is obtained between the virtual and real sensor, much better than before. Next we looked at the possibility of measuring the sound intensity with a virtual sensor. Conventional sound intensity measurements either require a tedious scanning procedure with an intensity probe or a large amount of individual measurements. Comparison is made with a reference measurement that is done with a sound intensity probe, and the results show a good agreement between the measured sound intensity and the sound intensity from the virtual sensor. Furthermore, we can calculate the sound intensity in the full field as a function of time, which we can use to calculate the radiated sound power. A question that we had while performing this experiment is its validity under non-ideal circumstances. When, for example, a virtual sensor has to be constructed for a vibrating machine in a big assembly hall, could this approach still be used although the acoustic conditions are not semi-anechoic? If so, this would be greatly enhancing the possible use cases. Therefore, we placed the setup with the oil pan in several environments, namely an office space and a big entrance hall. For these rooms, the experiment was repeated with the same numerical model as before, which gives the following results. Also, in these cases, the virtual sensor improves the results significantly, albeit to a lesser accuracy than the case in which the acoustic behavior is almost perfectly matched.
In this video, I've given you a glimpse of what I did during my PhD. I started by deriving time-stable, effective, reduced-order models for exterior vibroacoustic problems that consist of a combination of finite and infinite elements. These schemes are very useful in the design phase for vibroacoustic products and machines. Furthermore, I've shown how to create a virtual sensor that is able to estimate the sound intensity of a complex vibrating object using these reduced-order models, which gives promising results. Thank you for watching.